Yes, good morning, everybody.
Good morning, sir.
So let me give you the answers for the questions. So the first one, ARM architecture emerged before AVR and PIC architectures. The answer is true. The ARM architecture actually emerged somewhere in the early 80s, maybe somewhere around 82 or 83, between that time. Between 82 to 84, you can say it emerged. Of course, it did not gain that much popularity until the 90s. Okay, the early 90s, and it was in the mid 90s that I mean, the more popular architecture of the ARM, that is the ARM7, had released, and it had created a lot of waves in the world of embedded market. Okay, so V19HE701 is saying poll is not visible because I have stopped polling right now. Time is up. So all those who have answered have answered. Those who came in late, the poll is not visible anyway. Okay, so the ARM architecture emerged in the early 80s, whereas if you talk about the AVR and the PIC architecture, they emerged somewhere in the 90s. Somewhere in the early 90s, the AVR and the PIC architecture were introduced into the embedded market, but ARM architecture came way before them. Hence, the answer is true. Next, the second question, all ARM cores support pipelining. I already told you that ARM stands for Advanced Risk Machine, and risk architectures definitely will support pipelining. Hence, all the ARM cores will definitely support pipelining. So the answer is true. Next, coming down to the third one, all ARM cores support 32-bit address and data bus. Well, again, I told you ARM is not a single core, but it refers to a family of cores. In this family of cores, you're having single cores, you're having dual cores, you're having quad cores, you're having octa cores. Uh, Apart from that, you're having 32-bit core, that is 32-bit address bus, 32-bit data bus, okay, 32-bit instruction set. But if you go to the ARM Cortex series, there are 32-bit cores as well as 64-bit cores. So we're having 32-bit ARM cores and 64-bit ARM cores also. Hence, the statement all ARM cores support 32-bit address and data bus is not completely true. Okay, so it is false. Next, fourth one, pipelining in ARM maximizes the CPU throughput or instruction throughput. The number of instructions that can be executed per unit time can be increased through the help of the pipelining mechanism, which is supported in ARM. So the answer is true. Yes, it does maximize the instruction throughput. Next, fifth question. The acronym I2C stands for inter-integrated circuit. That is the first choice. Inter-integrated circuit is what it stands for. And next, the convention or industry standard speeds for I2C bus communication for standard mode. So there are some conventional speeds like 100 kilobits per second or 100 kilohertz, 200 kilobits per second, 400 kilobits per second or 400 kilohertz. You have 1 megabits per second or 1 megahertz, 3.4 megabits per second or 3.4 megahertz. You have 5 megabits per second or 5 megahertz. So among these various speeds, 100 kilobits per second or 100 megahertz is referred to as standard mode of communication. 400 kilohertz is referred to as fast mode of communication. 1 megabits per second or 1 megahertz is called as fast mode plus. 3.4 megabits per second is called as high speed mode. And the next one, that is 5 megabits per second, is called as ultra high speed mode or ultra fast mode, you can say, ultra high speed mode, you can say. So that is the sixth question. Coming down to the seventh question, which are related to the TCP/IP. So the first four questions were related to the ARM. The second and the fifth and the sixth question are related to the I2C protocol. Coming to the seventh question is related to the TCP/IP. So bridges are dash layer devices with respect to TCP/IP layers. So when we consider the TCP/IP model of communication or TCP/IP layered architecture, the bridges are what we call network interface layer devices. Okay, DC stands for data communication equipments. So bridges are dash layer DCEs. That means network interface layer DCEs with respect to TCP/IP layers. The next question is bridges are dash layer DCEs with respect to OSI model. When it comes to the OSI model, the answer is none of the above. Correct. So answer is none of the above. 59%. That is 24 people out of 41 people who had attempted had answered the questions correctly for that. Next, ninth question. Bridge functions in layer or layers dash of TCP/IP four-layered architecture. So the answer to this question is it functions in layer 2. Not layer 2, sorry, layer 1. It functions in layer 1. Layer 1 is called as the network interface layer. So bridges function in layer 1 of TCP/IP four-layered architecture. See the same question 7, 8, 9, and 10. These are almost very same questions, but slightly the presentation of the question is changing and the answer also is changing. That's the beauty of these four questions. So bridges function in layers dash of TCP/IP layered architecture. So in the TCP/IP layered architecture, we're having application layer, transport layer, internet layer, network interface layer. So bridges function in layer 1 with respect to the layer numbering method. And next again, bridges function in layers dash of TCP/IP 5-layered architecture. So I told you, depends on some text will try to explain, or some articles will try to explain TCP/IP using 4 layers. Some articles or text will try to explain TCP/IP in 5 layers. So both are correct. You just have to accept it and understand it. That's it. So when it is 5-layered, then you have layer 4, which is called as application. Layer 5 is called as application layer. Layer 4 will called as the transport layer. Layer 3 will be called as the internet layer. Layer 2 will be called as the data link layer. Next, you have layer 1, which is called as the physical layer, if you consider 5-layered architecture. So the bridge functions in layers 2 and layers 1. That is the answer for the question. Bridges function in layers 2 and layer 1. If you consider 5-layered architecture, it will function in layers 2 and layer 1. As a layer 2 device, it deals with MAC addresses. Okay. As a layer 2 device, it deals with MAC addresses. And as a layer 1 device, it deals with the physical signal, the signaling on the physical medium. So hence, it functions in both layer 2 and layer 1 with respect to 5-layered architecture. Whereas you consider 4-layered architecture, it will only function in layer 1. Layer 1 in 4-layered architecture is called as network interface layer. Somebody is asking the 6th question. The answer for the 6th question is the first one, 100 kilobits per second or 100 kilohertz. Okay, people. So that was the answers related to this polling. I hope this polling was helpful. I mean, these MCQs were helpful. Hello, people.
Yes,
Were
sir.
these MCQs helpful? Okay, good. So in the same way, prepare for tomorrow. Okay, somebody is asking, V 1987 M10 is asking why the question is multiple choice when the answer is one. We call it as MCQ questions, right? That is my understanding of MCQ. MCQs means multiple choice questions. We have multiple choice. Among the multiple choice, you have to select the correct choice. Okay, V1987 M10, that is my understanding of multiple choice. If the question, if there is a specific notification that this question will have more than one answer, or in the multiple choice question, if there are two answers, let's say A and B are two answers which are correct, then the third option may consist of A and B, like that. Okay, V19HE6. What is multiple choice questions? Normally, what is multiple choice questions? You're having MCQs are when you have a question and you're having four choices. So there are multiple choices down there. In that multiple choices, you have to select the correct choice, right? Unless if it is explicitly mentioned in the question that maybe there is more than one choice for this. Okay, so no problem. Let's see. Maybe in the next uh, test. Anyway, V19HE7 M10 has raised some question. Does everybody agree with him, or anybody else who is agreeing with V19HE7 M10 that the question seems to be a bit misleading for the multiple choice questions? Please, you can say something so that I can know whether, because that was my understanding. I took four choices, thinking that out of the four choice, one choice will be correct, unless if I explicitly mention in the question that if I give a hint in the question that uh, more than one choice is present over here. Okay, M10 V19HE7 M10. Others do not feel misleading. Only you feel that it is misleading. So maybe you have understood in a wrong way. But anyway, right now I've cleared it. So when I'm giving two choices or three choices or four choices, you have to select the correct choice among the uh, two or more choices available. Okay, V19HE7 M10. Do we have an understanding between you and me right now? Okay then. Right. So tomorrow again, you'll have a few questions on I2C protocol, questions on TCP/IP, and questions on what we call uh, ARM. So please be on your heels or toes to be ready to answer the questions. So I'm going to switch over so that I can share the slide and continue the discussion. Okay. So just give me a moment. Let me just bring up the. Okay, yes, guys. Yes, people. Yesterday we had discussed about the memory, what you call the data flow model. So, proceeding with the next slide after the data flow model. Right. So, proceeding with the next slide after the data flow model. Right now, just a briefing about the registers right now. As already mentioned that the ARM7 core is having support for 37 core registers. So mind you, these are the core registers. And when you go to the microcontroller designed using the ARM7 core, so the microcontroller designed using ARM7 core will come with an additional set of registers, which we call as special function registers for peripherals, or you can say peripheral SFRs, peripheral special function registers. So the number of peripheral special function registers will be varying from one microcontroller to another microcontroller in a particular family of microcontrollers. Suppose if I take ARM7 TDMI-S implementation and a family of microcontrollers has been developed by Philips, then whatever registers for the peripheral SFRs are available, these will tend to be different from one member to another member, as well as when ARM7 TDMI ARM7 TDMI-S implementation is used in Atmel family of ARM7 TDMI based microcontrollers, then the peripheral SFRs will be varying. So the peripheral SFRs will vary from family to family and from member in a family to another member in a family. So they will vary based on the availability of the peripherals. But as far as the core is concerned, the 37 registers of the ARM7 core remain same irrespective of the implementation. So uh, if it is ARM7 TDMI or if it is ARM720, both the implementation will have the same 37 core registers. So the ARM7 has support for 37 core registers, and out of 37 core registers, 16 registers I had already mentioned are accessible in the modes of operations. So you have 7 modes of operations. At a point of time, the ARM core can only be in any one of the 7 modes of operations. And whichever mode of operation it is at a point of time, it can only access 16 registers. So there are some set of registers in this 16 registers which are common to all the modes, common resources, and some registers which will be unique for this mode and not available in other modes. So brief description about the registers. 16 registers which are numbered from R0 to R15. So the first 13 registers which are numbered from R0 to R12 are called as the general purpose registers. So the name general purpose registers implies that these registers are used for general purpose operations in the ARM core. Okay, so they can be used for holding data for processing, and they can be used for pointing to some memory locations to access information indirectly like that. So general purpose. When we come to the next registers, R13 is a special register, which is a register of the core, and that special register is called as the stack pointer register. And I'm sure all of you are aware about what is a stack pointer register. Okay, so a stack pointer register is a register which always points to the top of the stack. It's a register which always points to the top of the stack. That's what is a stack pointer register. In 805 architecture, your stack is an upgrowing stack. Here in the ARM architecture, the stack pointer is also an upgrowing stack. Okay. Only thing is, in your 8051, your stack pointer is having an address there. Okay, as stack pointer's address, I think, is 81H in 805 architecture. Here, R13 stack pointer does not have any address, so it is just accessible through a register name, that is R13, or simply sometimes also called as SP register. So the opcode is available to access R13 register, but not by address. Okay, that's about stack pointer register. And next you have R14 register, which is called as subroutine link register. So subroutine link register is a register which holds the return address of the next instruction to be executed whenever the CPU branches from a call subroutine. So if a call subroutine is invoked using a call statement, okay, a call statement or a branch to a call routine, then what happens? The return address of the next instruction to be executed after completing the subroutine, that return address is getting stored in the register called as subroutine link register. That is called as R14, or sometimes it is also called as LR, which stands for link register. Next, you have the PC. PC stands for program counter. So the program counter in ARM architecture is a register which you can access. You can write a value into the program counter directly, and you can read the value at any point of time from the program counter. Hence, unlike 8051, we do not have a direct instruction or address to access the program counter. We need to access the program counter indirectly because there is no direct method. Here in ARM architecture, it has what we call a direct method by using the name called as R15 or program counter. So this was a briefing about the ARM7 register set. Any questions over here, please, you can raise so that if I analyze or realize that you have no doubts, I can move ahead with the next slide. Yes, correct. HE7D12, correct. Registers here, these 37 registers in ARM, that is the core registers, do not have any specific addresses. Unlike 8051, where registers of bank 0, R0 to R7 use address 00 to 07. R0 to R7 registers of bank 1 use the address 08 to 0F, whereas registers of bank 2, R0 to R7 use the address 10 to 17, and registers of bank 3 use the address 18 to 1F. Here, the registers of the ARM, that is the core registers of the ARM, 37 core registers of ARM do not use any addresses for accessibility. Yes. Yes, V19H7D2, we access it by name, R0 to R15. You can also use sometimes the symbol SP for stack pointer and LR for link register, as well as PC for program counter. So either you can use the name R13, 14, 15, or you can use a name or symbol SP, LR, and program counter. Any more questions over here, please, from your side? Anybody else has any questions regarding the registers? Okay, I'm moving ahead then. Okay, other registers is used for other operations. What do you mean by other registers? D2, D12, sorry. Didn't understand your question. What do you mean by other registers? Could you please clarify your question? R16 to R36? No, we do not have any register symbols by the name R16 to R36. The register symbols are named as R0 to R15 only. Though there are 37 registers, they are named as R0 to R15 only. So in any mode of operation, if you go for user mode, you can access R0 to R15. If you go for supervisor mode, R0 to R15. Abort mode, R0 to R15, like that. So the register names are restricted symbolically from R0 to R15, even though 37 registers are available. Okay. Anybody having any more questions? Please look at the next slide. Just have a look at the next slide, which is talking about a register R16, which is called as CPSR. So I mean, the symbol R16 is not programmatically accessed like that. It is accessed using the CPSR. But it is just numbered as R16 for information here right now. So R16 register means R0 to R15 are the accessible registers of a mode of operation. And you have CPSR register, that is called as current program status register. You don't access it as R16 register. You only access it by using the symbol CPSR. So the CPSR current program status register is also called as the flag register of 8051 architecture. Okay, the flag register of flag register of the ARM7 TDMI, ARM7 architecture. Very sorry, flag register of the ARM7 architecture. Just like in 8051, you have a PSW register. Here, this is called as the current program status register. So in this current program status register, it is a 32-bit register, but out of 32 bits, uh, these 32 bits are divided as follows. The first 8 bits, that is bit number 0 to bit number 7, starting from the least significant bit, the first 8 bits, that is bit 0 to bit 7, is called as control field or control bits. Then the next 8 bits, that is bit number 8 to bit number 15, is called as status bits. And the next 8 bits, that is bit number 16 to bit number 23, is called as uh, extension bits. One second, I think I just misplaced it here. Control field, extension field. Sorry, bit number 8 to bit number 15 is called as extension field, and bit number 16 to bit number 23 is called as status field. And then bit number 24 to bit number 31 is called as flags fields. So in these 32-bit register, as of now, only the 2 fields are available in ARM7 TDM, ARM7 core. They are control field, which is 8 bits, 0 to 7 are available, and extension field is not available, and status field is not available, means it is reserved or unused. And then in the flags field, which is bit number 23 to bit number 24 to bit number 31, the most significant bits in the flags field is available, starting from bit number 28 towards 31. So bit number 28 is called as the overflow flag bit. Bit number 29 is called as the carry or borrow flag bit. Then bit number 30 is called as the zero flag. And finally, bit number 31 is called as the negative flag, also called as sign flag. You can think of it as a sign flag. So the first 5 bits, that is bit number 0 to bit number 4, these are called as the mode selection or mode configuration bits, because the ARM core is having the ARM7 core is able to operate in 7 modes of operation. So the primary need of a mode of operation is to protect the registers such that the total number of registers per mode are restricted, and registers used in one mode may not be accessible in another mode because of the security feature. Hence, there will be some set of registers which are common to all the modes and few registers which will be accessible only in that specific mode but not in any other mode. These are called as the secure registers, you can say. Okay, I hope you're following so far. So the first 5 bits, M0 to M4, these are the mode selection or mode configuration bits, and the mode selection or mode configuration bits are as follows. Just please look at this slide which comes after this. Just have a look at this slide for a few seconds. Okay, people, I hope you have had a view of this slide. So this slide is giving us information about what is the binary combination in the bits 0 to 4 of the CPSR register, which will decide what is the mode of operation, which is going to decide what is the mode of operation. So you can see here, I'm just, I'll use the annotation here. So here, if I take it in terms of hexadecimal, this is 0x 1 7. This is 0x 1 1. This is 0x 1 2. This is 0x 1 3. This is 0x 1 f. This is 0x 1 1b, and this is 0x 1 0. Are you following, people? Please let me know. So these are just binary combinations which have to be used or placed inside the bits M0 to M4, which will decide what is the mode of operation the CPU is in. Is it in user mode, or is it in supervisor mode, or is it in a bot mode, or is it in FIQ mode or IRQ mode, like that. So you have the order which begins with 0x10, then it moves to 0x11, 0x12, 0x 0x10, 11, 12, 13. Next, after 13, there is 17, and then you have what we call 1b and 1f. So if I can put it like this in this order also, 1, and then you have 2, you have 3. In increasing order, I'm putting it into increasing order of number or magnitude. So next 4. Okay, after that you have 5. After that you have 6, and lastly 7. So these are the 7 modes of operations. First mode with the lower number is user mode, which is 0x10. Second with the next higher number is past interrupt. So if I just put the letters like this, first is U, second is F, third is I, next fourth is S, next fifth is A, and sixth is U again, and finally uh, seventh is S. UFISAUS. You can remember this in the order of increasing. So the number starts from 0x10, then moves on to 0x11, then moves on to 0x12, then moves on to 0x13. After 0x13, there is a jump to 0x17. After 17, you have a jump to 0x11. Sorry, 17. After that, 1B. And after that, you have what we call 1F. So if you follow this order, UFISAUS is a symbolic, letter order from lower number to higher number. So you can try to create a sentence for this also. UFISAUS. You can say user find it simple and understanding system. Okay, guys, look at this sentence which I've just created or synthesized. I've synthesized the sentence using the letters UFISAUS, UFISAUS, UFISAUS. User find it simple and understanding system. User find it simple and understanding system. This is one sentence. You can also create another sentence. So the sentence creation is your wish, how you create and how you remember. UFISAUS, user find it simple and understanding system. Or I can also maybe say user find it simply aspiring understanding system. So it's just a matter of a sentence which you have to create to remember the order of the what we call modes in increasing order of configuration. Hello people, are you getting this discussion so far? If any questions, you can raise now. I have discussed about the 5 modes briefly already in the previous classes. Here it's just a discussion about what are the values to be loaded into the 5 bits of the CPSR register for the mode of operation of ARM to be decided. I'll wait for a minute, hoping that if you have any question, you can come out with question regarding the 2 or 3 slides which I've shown. Yes, people, I'm waiting for any questions regarding the first 3 slides which I have shown in the second series of slides. Can I go ahead if no questions? Okay, I'm moving ahead then. Nobody is asking any questions, so move ahead now. So coming back to the what we call a register. So what you can see here right now is we have discussed about the M0 to M4 bit status or bit values for the mode selection. Next, T bit. The T bit stands for the thumb state bit, means whether the ARM processor is executing an instruction which is an ARM instruction set, or it is going to execute an instruction which is a thumb instruction set. If the ARM processor is executing an instruction which is ARM instruction set, the status of the T bit, thumb bit, will be 0. Whenever the T bit is set to 1, it will be indicating that the ARM processor will be uh, decoding an instruction as a thumb instruction and execute that. So whatever instructions are fetched from the code section, whether they should be decoded, that is interpreted as an ARM instruction, or should be interpreted as a thumb instruction, will be decided based on the status of T bit. If T bit is 0, it means it will interpret or decode it as a ARM instruction. If the T bit is set to 1, if the T bit is set to 1, it implies that it will be decoded or interpreted as thumb instruction. If T bit is set to 0, it will be decoded or interpreted as an ARM instruction. That is the purpose of the T bit. Is the T bit understood, please? M0 to M4 bits are understood and T bit understood. Please confirm. Next, you have the F bit and the I bit. So the status of the F bit and I bit by default will be 1. Default status of the F bit and I bit is 1. If the F bit and I bit is 1, it implies that both FIQ interrupt as well as the IRQ interrupts are disabled. To enable the interrupts FIQ and IRQ to be entertainable by the CPU, so that when those interrupts are raised, the CPU should be able to entertain the ISR or handle the ISR. So for that particular purpose, the F and I bit should be set to 0. Sorry, yeah, should be set to 0. Very sorry. Sometimes it gets confused with the 8051 this thing. So 8051, whenever you want to activate an interrupt in 8051 architecture, we need to set the interrupt bit to 1 to allow or to enable the interrupt to occur. Here, to allow or enable the interrupt to occur, we have to set the INF bit to what we call 0. So clearing the I and F bit to 0 indicates that interrupt will be allowed to occur. If I and F bit are set to 1, it indicates that interrupts are not allowed to occur. They will not be entertainable. This is about FIQ disable bit and FIQ enable. So enabling means writing 0 to the I and F bits. Disabling means writing ones to the I and F bit. Is the I and F bit understood? Please confirm. Is the I and F bit of the flag register understood? Okay, so that completes the control field. Then moving to the flags field, in which you're having 8 bits, bit number 24 to 31. Among 24 to 31, bit number 24, 25, and 26 are not available. Hence, they are called as reserve bits. Bit number 28 is called as the overflow bit. Overflow bit means in an arithmetic operation, whenever you're dealing with 32-bit data, if there is a result which brings the, if there is a computation which brings the result beyond 31-bit range. So overflow flag is used for signed numbers. When we're dealing with signed numbers, the magnitude of the signed numbers range in case of 32-bit, and the magnitude of unsigned numbers range will be different in the case of 32-bit as compared to the 8051 uh, architecture. So in 8051 architecture, in the 8051 architecture, your signed range was varying from -127 to +128. True or false? or was it ranging from minus 128 to plus 127? What is the sign range for 8-bit? Minus 127 to plus 128 or minus 128 to plus 127? Please answer this question. Minus 127 to plus 127. Minus 128 to plus 127. Okay, very good. So what will be the signed range for negative to positive integers for 32-bit? Can you please express the answer and send it to me? The signed range for negative to positive numbers for a 32-bit CPU ranges from what to what? Minus 2 giga to plus 2 giga. Okay, good. So can you express this range minus 2 giga to plus 2 giga in terms of powers of 2? Can you express this range minus 2 giga to plus 2 giga in terms of powers of 2? Means positive, I mean the range in terms of powers of 2. Please can you try to express it? I'm waiting for the answer. Two power 32 is not correct. 2 power 32 is not correct. Minus 2 power 32 to 2 power 32 minus 1, that is not correct. Please again try to verify. Minus 2 power 31 to plus 2 power 31. Okay, that is a bit better. Minus 2 power 31 to plus 2 power 31. Okay. So what is the range of now positive numbers? 0 to 2 power 31. What is the range of the positive numbers? 0 to 2 power 31 or 0 to 2 power 31 minus 1? The answer for positive sign numbers. Positive sign numbers, please. 0 to 2 power 31 minus 1, correct. 0 to 2 power 31 minus 1 is the range of positive sign numbers. What about negative sign numbers? What is the range? What is the range of negative sign numbers? Please, can you tell me? Minus 2 power 32 to 0 is wrong. Minus 2 power 31 to 0 is also wrong. Yes, tell me the correct answer. This is also wrong. Minus 2 power 31 to 0 is not correct. That's your answer. Minus 2 power 31 to minus 1 is the range of negative sign numbers. Did you get it, everybody? Okay, guys. Yes, people, did you get it? So 0 is coming under the positive one. So 0 to 2 power 31 minus 1 is the positive range. Negative range is minus 2 power 31 to minus 1. So whenever we are dealing with some kind of arithmetic operations in which the result of an operation goes from a signed range. I mean, it goes from negative numbers range to positive numbers range, or it comes from positive numbers range to negative numbers range. In that kind of situation, we say that the overflow flag will be set to 1. So when the result of the operation, arithmetic operation, exceeds the sign range, when the result of the arithmetic operation exceeds the sign range, then we say that the overflow flag will be set to 1. That's about overflow flag. Next, you have carry flag. Carry flag or borrow flag is the flag which comes after 32 bits. Means whenever two 32-bit numbers are added, if the result is greater than 32 bits, that greater result than 32 bits will be treated as a carry bit. Otherwise, if you're trying to subtract, let us say 0 minus 1 in terms of 32 bits, if you're trying to subtract 0 minus 1 in terms of 32 bits, you will get the answer as minus 1. In terms of 32 bits, minus 1 is going to be all 32 bits will be ones. Hence, in this kind of situation, the carry flag, which is now called as the borrow flag in the subtraction operations, will be set to 1. So subtraction is the same thing as uh, 2's complement addition of a given number. Suppose if I say 5 minus 2, so minus 2 number will actually be taken as 2's complement, and that will be added to the first number. So carry flag and borrow flag are same. The carry flag or borrow flags are those flags which will be set when the result of the addition exceeds beyond 32 bit. Then you have zero flag, result of arithmetic operation, or the result of some operation is going to be 0. Then the zero flag is going to be set to 1 to indicate that the end result is 0. So we should take decision. Coming to the last one, negative flag, which is also called as the sign flag. When the result of some arithmetic operation is, let us say, a negative result. So 1 minus 2 is minus 1 is a negative result. Then the negative flag or the sign flag would be set to indicate that the result is negative. So that is the briefing about what we call CPSR, current program status register, which is also called as a flag register. I'm going to pause for a few seconds or a minute. Anybody wants to ask questions within this few seconds or minutes, please frame your questions and try to ask. I'll be waiting here. Okay, the carry flag and the overflow flag I've explained. Zero flag is a flag which will be set when the result of an operation is going to be 0. Okay, whenever you talk about the result of some arithmetic operation, if the result of the arithmetic operation is going to be 0, the end result is 0. Suppose if I'm adding the content of two registers, if I'm going to add the content of two registers and the result of the AND operation is going to be 0, then the 0 flag will be set to 1. If I'm going to subtract two numbers and the result of the subtraction is going to be 0, then the zero flag will be set to 1. Then you have N flag. N flag is called as the negative flag. It is something like also called as the sign flag. So the N flag, which is negative flag or less than flag, is also called as the sign flag. When the result of an arithmetic operation is negative, means suppose if I subtract a number simply 1 minus 2, 1 minus 2 gives a result of minus 1. So whenever the result is minus 1, automatically the negative flag will be set to 1 to indicate that the result of the arithmetic operation is negative. So when the most significant bit of a 32-bit, when the most significant bit of a 32-bit result, when the most significant bit of a 32-bit result is 1, then for a 32-bit, most significant bit being 1 indicates negative result. Hence, the N flag would be set to 1. Is this understood, people? Okay. Okay. Right. Just give me a few seconds, please. I'm just trying to make some small arrangement. Okay. Okay, people. Any more questions regarding the flags right now? So I can move ahead now. So as I told you, the ARM core uses the CPSR to monitor what we call the different types of uh, flags. So we have flags related to mode of operation. We have flags related to the interrupt enabling or disabling, flags related to the whether the CPU is going to interpret the instructions as an ARM instruction or thumb instruction, like that. We have the arithmetic flags, carry flag, overflow flag, zero flag, negative flag or sign flag, like that. Okay. So as already mentioned that the flag register is divided into 4 fields, that is the control field, extension field, status field, and flag field. I mentioned that. Now, apart from the CPSR register, which is only one register, one and only one register in the ARM7 core, uh, and this register remains a common register for all the 7 modes of operations, namely the user mode and the abort mode and the FIQ mode, that is fast interrupt request mode and interrupt request mode, and the system mode and the supervisor mode. Okay, and what is the other mode? The undefined mode. So for all these 7 modes of operations, the CPSR register remains one register only for all these modes of operations. But we have a type of register called as SPSR. SPSR stands for Saved Program Register. Am I audible, please? Okay, because I just made some small arrangement where I'm not sitting and taking the class, but I've tried to increase the height of my laptop by putting a stool on my table, and I'm standing and taking the class just to emulate a classroom style of taking a class. That's why I just took a few seconds to make that arrangement. But because frankly speaking, sitting and taking the class doesn't feel like I'm taking the class always. It's okay to sit and write a code, but sit and take the class is not that easy. So I made some arrangements to stand and take the class. Okay, so SPSR, that is Saved Program Status Register, is a type of register which is used for storing the copy of the CPSR register whenever a mode change takes place. So when the CPU changes its mode of operation, let us say from user mode to FIQ mode, then the user mode status available in CPSR gets copied into the SPSR register of the what we call FIQ mode. Similarly, if from user mode CPU enters into supervisor mode, then the CPSR status of user mode gets copied into SPSR register of supervisor mode. So out of the seven modes of operations, the five modes of operations have duplicate uh, SPSRs, means they have uh, more than one SPSR. So ARM7 is having more than one SPSR, and there are up to five SPSRs additionally available, but there is only one CPSR. So these five SPSRs are available for the five modes of operations, excepting two modes of operations. So that's about SPSR. Saved Program Status Register is basically a register used to hold the value of CPSR of the user mode of operation whenever a CPU switches from user mode to any of the other five modes of operations. So just hold on and I'll show you a figure. So please observe this figure for a few seconds. You will not get it in the first shot. Just observe this figure for a few seconds, then I will discuss on the figure. Okay, people, have you observed the figure closely? So can you, those people who have observed the figure closely, can you mention how many modes are given here in this figure? Can you mention how many modes are given in this figure? 7 modes are given. So one what do you say, horizontal, one vertical box, okay, one vertical row, sorry, one vertical column is given the name as system mode as well as user mode, system and user mode, because system and user modes are two modes. So the modes are named as system mode and user mode. They are different modes, but the thing about the two modes is they use the same set of common registers. So the register set, the core register set are common among both these two modes of operation. System and user mode use the register set R0 to R15, okay, including the CPSR. See, I already told you CPSR is a common register for all the modes. So we have R0 to R15 there. Is it visible? First of all, please tell me. I mean, visibility wise, is it okay? You're able to see it clearly? Okay. So the system and user mode is having.
No, sir. Can you increase the size?
Okay, I'll increase the size. That's what I just wanted to be clear. Just a moment. F5 is it? Okay, I hope now it is clear. So
Yes, sir, clear.
So we have the system in user mode in which R0 to R15 registers are given there, totally 16 registers. In addition to that 16 registers, you have the flag register called as CPSR. So that is 17 registers in totality for system and user mode. Next, coming to the FIQ mode, as you can see here, in the FIQ mode, you have some shaded what we call registers there. So those shaded registers are actually indicating what we call the uh, banked registers of that mode of operation. So physically the registers are different, which and they are just named as R8 underscore FIQ to R14 underscore FIQ. So it's just a name given to them to make you differentiate that R8 underscore FIQ to R14 underscore FIQ are physically different registers, or they are also called as the banked registers. Whereas R0 to R7 are the common registers, which are the same registers of R0 to R7 of system and user mode. And R15 is also the common register, and CPSR is also the common register. So the shaded registers you can see there, R8 underscore FIQ to R14 underscore FIQ, as well as SPSR underscore FIQ, are the banked registers or separately physical registers. So hence, here also in the FIQ mode, you're having what we call 16 registers. And in addition to that 16 registers, you have what we call the common register CPSR, and you have SPSR. So whenever from system and user mode, a switch of the core takes place to FIQ mode, then the value of the CPSR, I'm just annotating, one second, please. Okay. Uh, the CPSR register gets copied into the SPSR register of FIQ mode. So most of the time the CPU will be in the system, it will be in the user mode, or maybe sometimes it may be in the system. Most of the time it will be in the user mode. I already mentioned that. Okay, so more than 95% of the time the system will be in the user mode. From user mode, or else from system mode, if it switches to FIQ mode when an interrupt occurs, so it switches to FIQ mode automatically whenever an interrupt occurs. That time the CPSR gets automatically copied into SPSR. So additionally, we are having here now 17 registers. Okay. Then here you're having 1, 2, 3, 4, 5, 6, 7, 8. 8 registers here. So 17 plus 8, that makes it 25 registers so far. Next, supervisor mode. As you can see there, in the supervisor mode, R0 to R12 are the same common registers, but R13 and R14 and stack SPSR register are again banked registers. So we have 25 plus 3 registers, that makes it 28 registers. And then coming to abort mode, again R0 to R12 are the common registers. Then R13, R14 and SPSR are again separate physical banked registers. So we have 29, 30, 31 registers up till now count. Then 30 IRQ mode, you're having 32, 33, 34. Okay. Then 35, 36, 37. So totally 37 registers are available in the core, and this is how they are distributed in terms of accessibility for the 7 modes of operations. Did you people get this discussion? If so, okay, we continue. If not, you can raise your doubts. I'm waiting for any doubts if you have any regarding the discussion of the registers. So we have 5 SPSRs. Okay, we are having 5 SPSRs. We are having means we are having 5 SPSRs, then we are having 5 new R13 registers, which is also called as stack pointer registers. We have 5 new R14 registers, which are also called as the link registers, subroutine link registers. So 5, 5, 5, that makes it 15. Okay, then apart from 15, then you have 16, 17, 18, 19, 20. I'm trying to explain this in a different way also. Okay, V19HE7, V8, I'm going to explain it once again. First, the way I had explained it. So system and user mode is having, as you can see there, 17 registers. Okay, system and user mode is having 17 registers, in which R0 to R15 are accessible by the programmer. And CPSR is about the status register, about CPU status. Of course, it is also accessible by the programmer, but it's not a general purpose registers like that. Okay, so it's a flag register. So R0 to R15, that is 16 registers of the system and user mode, are common registers for system and user mode. Next, you have R0 to R7. These are also common registers of FIQ mode. But R8 to R14, these are banked registers of FIQ mode. They are only available in FIQ mode, but not available in any other modes. And SPSR underscore FIQ is also a banked register of the FIQ mode. Hence, you have about 8 banked registers of in FIQ mode. You have about 8 banked, 1, 2, 3, 4, 5, 6, 7, 8. 8 banked registers in FIQ mode. You have 3 banked registers, namely R13 SVC and R14 SVC and SPSR SVC in supervisor mode. Okay, then you have another 3 banked registers in abort mode. So banked registers are those registers which are uniquely accessible in that mode of operation, but not other modes. The unbanked registers are not shaded. Okay, there is no shading for the unbanked registers. They are common registers. So supervisor mode, abort mode, and IRQ mode and undefined mode. Okay, supervisor mode, abort mode, IRQ mode, and undefined mode, and FIQ mode. R13 and R14 and SPCRs are new registers. So we have new SPCR register for FIQ mode, supervisor mode, abort mode, IRQ mode, undefined mode. You're having new stack pointer registers for FIQ mode, supervisor mode, abort mode, IRQ mode, undefined mode, as well as new link register, subroutine link register for FIQ mode, supervisor mode, abort mode, IRQ mode, undefined mode. Hence, 5 new SPSRs, 5 new stack pointers, and 5 new link registers. So 5, 5, 5, that makes it 15 registers, okay, which are there. In addition to the 15 registers, so consider the registers R8 to R12 over here. So I'm just using the coloring method over here. Just one second. Okay, guys. So the blue encircled area in totality is having 15 registers, and the red crossed line area is having around 5 registers. So 15 plus 5 is 20, and this complete is 17 registers. So 20 plus 17 is making it 37 registers. So in totality, we are having 37 registers, of which 17 registers of system and user mode, and additionally new registers in FIQ mode, supervisor mode, abort mode, IRQ mode, undefined mode. Is it understood, people? Anything else which is confusing you? Okay, V19 He7 D12, R0 to R15, R0 to R15. Next you have R16, R0 to R15 is 16 registers. Okay, then 5 SPSRs, correct. 1 CPSR, correct. And 5 R13 registers, 5 R14 registers, and 5 registers R8 to R12. So totally 37 registers, correct. Yes, V19 He7 D12, correct. Can I go ahead with the discussion or any more queries on this picture? Okay then. So fine. Right. So let's have a break. It's about 1 second. Right. It's about 11:43. So let's meet at 12 o'clock and continue our discussion with I2C protocol. Okay, guys, we meet at 12 o'clock.